Hello, I'm Warren Powell, and I'm going to be talking about the next generation of AI, a universal framework for sequential decision problems. I'd like to express my warm appreciation to Chris Singh for inviting me to talk before his global program on innovating the digital economy. This is sort of a tapestry of problems I've worked on in my career. Did a lot of work in truckload trucking in the upper left, worked extensively for Norfolk Southern with railroads, some air cargo, worked in manufacturing. I ran an energy lab for 10 years. Fabulous experience doing that. This was all done through Castle Laboratory, which is my academic lab that had a unique partnership with industry where we would actually contract to write software. I had professional programmers who would develop code so that we could implement models in the field and learn from that. And it would be sort of a back and forth experience. So this is what is driving everything in this talk today. Now, everything I did could be described as working with human processes, and every aspect of human processes deals with humans making decisions in the presence of uncertainty because information keeps arriving. Now, what we're trying to do is achieve goals like increase profits, reduce costs. Maybe I want to increase the strength of a material or reduce illness or minimize waste. Now, the defining slide of this entire talk is if you want to run a better supply chain, energy system, health system, anything, you have to make better decisions. So everything in this talk is all about making decisions because we want to do something better. So I'm going to start with the 7 levels of AI because we're seeing a lot with artificial intelligence. And what we're trying to do is to do smarter things with computers. So here are my 7 levels of AI. The first 4 levels are focused on making computers behave like humans, which in computer science is considered a very lofty goal to be as intelligent as a human. Now, the next levels are making computers smarter than humans. And so what I'm going to do is eventually focus on levels 5 and 6, but a little bit of level 7. Now, level 1, this is AI in the 1970s and 80s. This is rule-based systems. This was the basis of expert systems. By the late 1980s, it was viewed as a complete failure because it was supposed to take over the world. All the stuff you hear today was being said back then. In fact, rule-based systems are very successful and they're still being used today. Now, levels 2, 3, and 4 all have to do with machine learning, but I put them in different levels because they're really quite different. So level 2 is what it used to be called statistics. We're taking a function and fitting it to data to forecast demand. We saw the early use of neural networks. Now, level 3 really emerged in 2010 with image recognition. There was the first use of deep neural networks where we would train a computer to recognize a visual image or a voice pattern. This is the Hey Siri. Now, level 4 this is what has just exploded on the scene with the large language models, truly another generation of machine learning. Now, level 5, this is deterministic optimization. This is where we're going to take a problem like finding the best path to a network. If I'm at node 2, go to node 5. Or maybe I have a high-dimensional problem of looking at all the permutations and combinations of where to locate warehouses and come up with the best design. All of this uses a language called math programming, where we have decision variables x, which can be a 0, 1, or a big vector. Usually it's a big vector. We have an objective function that we're trying to minimize or maximize. And we have a set of equations that determine what are the feasible values of x, because otherwise I could just set x to 0 everywhere. And so what I want to do is to be able to say, what are the allowable values of x? Now, this is a language spoken around the world. Many books communicate the same core theory using the same notation, a number of software packages that are widely used, commercially available. So this is a very successful field. Now let's go to level 6. So let's go back to my tapestry. We have all these problems. Behind every one of these problems are decisions. So every one of these boxes poses a question where to answer the question, I have to make a choice, and I want to make the best choice, okay? So that requires having a metric and then choosing the best of the set of choices. Now, after I make a decision, information arrives that I didn't know when I made the decision. So this creates what we call sequential decision problems, where we make a decision, then information arrives, then I make another decision and information. And the information that arrives in the future is not known when I make the earlier decisions. So examples, inventory management. I may place an order for inventory that could arrive quickly or well into the future. Then I see various market demands, after which I place more inventory orders. This comes in a wide range of different flavors. My company, Optimal Dynamics, we're assigning the blue circles are drivers, the red squares are loads. I'm assigning drivers to loads. Loads are being called in dynamically over time. This is a very high dimensional decision that's evolving over time under very stochastic information. Maybe we're testing new vaccines and we want to know what dosage or which people to give the vaccine to as we see how the people respond and which people accept vaccination. Finally, financial trading. Here I'm buying and selling different assets as the market is changing prices. Now, here's a problem that is traditionally viewed as one of these static deterministic problems. Which warehouses should I have to support my supply chain network? Now, the thing is, you don't just solve this once. You're solving this maybe every quarter or every year. It's dynamically changing. The decisions will remain in place for multiple years, maybe a decade or more. So this is also a highly stochastic dynamic problem. Now, of all the sequential decision problems, this is by far the most common. I have a set of choices. I could have 2 choices. I could have 10. I can have 10,000, okay? But I have different types of choices, and I have to enumerate my choices. Sometimes these are obvious. In many problems, they're not. So simply coming up with a set of choices can be a challenge. But the real challenge is I don't know how well they all work. So I have possibly a high level of uncertainty about this performance. And one thing I can do is additional work to collect information, but another is to just try something, see how it works, and then make another decision the next time. Now, this is what I like to call my jungle of stochastic optimization. All of these books work on sequential decision problems, but with completely different styles. There's about 8 fundamentally different notational systems. They don't even write the problem the same way. They don't agree what an objective function is. They don't agree what we're optimizing over. So this is a real mess. And by the way, there's very little software. Major exception might be the introduction to decision analysis, because there is decision tree software. The math is really quite arcane, whereas deterministic optimization is taught widely to undergraduates. This tends to be strictly PhD level material for mathematically sophisticated audiences. Now, all of these books deal with sequential decision problems and uncertainty. Almost no commercial software packages that businesses can use. And businesses have largely had to resort to the creative use of deterministic models for solving these stochastic dynamic problems. Okay, level 7. Level 7 is my newest level. This is integrated LLMs and decisions. So we've seen a lot with large language models. So here is a flow of information. Everything yellow here is a flow of information coming in from the real world, sometimes helped along by large language models to interpret, do data mapping. Sometimes they're going through machine learning models to do statistical estimation, to fill in gaps when I don't know something. Now, all of this feeds into policies. I sometimes call these decision functions, the green boxes. And these are where decisions are made. And after the decisions are made, we may go through another layer of large language models as we go to implement these decisions. So this is, I think, this is the next generation of AI, where the advanced machine learning models, especially the large language models, get integrated with decision making. My talk will mainly focus on the decision making. Okay, before we get to anything mathematical, I'm going to start with the problem of framing the problem. Now, the way we've generally approached problems, let's take some problem in the real world and we want to put it on the computer because it'll do all sorts of magical things. And that means we have to go through the step of creating a mathematical model. Now, to do that, we say, oh, well, now we need a math guy who's going to come in and translate the real problem into the math model so we can put it on the computer. This is the problem. This style, which I have used most of my career, has a fundamental flaw, and I call it expertise filtering. Now, each of these 6 boxes represents an entire field, a major area of expertise: machine learning, whole field of people doing it, Monte Carlo simulations, there's decision tree experts, big community on math programming. Now, the stochastic search is so universal Uh, but that's sort of a less well-defined community, even though the problem is widely used in practice. Now, what these people do with this expertise is they tend to look at the problems, the real-world problems, through the lens of how they've been trained. And this is the limitation. So I'm going to propose a new approach. I call this the skill cycle. We're going to start in the upper left-hand corner describing the problem. Now, maybe this is a business problem. It could be a health problem, something in manufacturing. Let's just assume it's a basic business problem. Now, in the upper right-hand corner, this is a group of students that I've been working with at Rutgers in their supply chain management department. These are all bright, capable students. They're not mathematical. They don't pound computers. They can use a computer, but they don't write code. And I think this is a group of students that has a skill set that I would like to take advantage of called framing the problem. And I'm going to spend time on that particular slide. Now, framing the problem requires no math and no data. Okay? It requires insights and the ability to ask the right questions of the domain experts in the upper left-hand corner. Now, there are three questions I'm going to introduce you to. I'm going to talk you through the framing process. Now, there are many decisions out there, and I think that quite often simply going through the framing process may help you solve your problem. Okay, because the simple fact is we don't put every decision through analysis. Now, when we do have to go through analysis, we're going to come down, we're going to use what I call the universal modeling framework. That is the only place I have any math in this talk, and I'm going to give you a quick explanation of this slide, which is the step before we go to a computer, which could be nothing more than an Excel spreadsheet or maybe something more advanced. Okay, now let me pause here and talk about when we're trying to solve a problem. I have found that problems tend to come in two flavors. Metric focused problems is when we have a goal. I want to maximize the stock price or increase sales or increase the strength of material, something. I have a metric, I have goals or multiple goals. I don't necessarily know upfront what the decisions are to achieve those. Or decision-focused problems where I do know the decision. I want to know where I should put warehouses or how to route trucks or what price to set. I know the decision. Now, I may also have an idea of the metrics in these more complex problems, even forming the problem. Now, I'm going to blend these two because we need both of these. I need metrics and I want to make decisions. Now, this one slide is the framing slide. So if you want to run a better anything, you have to make better decisions. The path to improvement starts by answering three questions. What are your performance metrics? What decisions do you have to make and who makes them? And what are the sources of uncertainty? And if you go to tinyurl.com/doingbetterppt, you can download this slide. Download it, print it out, put it up next to your desk. This should be the defining problem. This slide requires no math and no data. However, posing it is best done by people who don't have formal training in analytics because otherwise when you have that, you have a tendency to bias your answers. So this is best done by people who know how to ask the questions and work with domain experts to get these answers. Now, as I step through my framing, I'm going to use I'm not going to call it a little inventory problem. This is actually sort of a realistic, messy one. I'm getting product from Asia to fill inventories at a big warehouse in Atlanta, and I have various decisions of who to order from and how much to order. I have to deal with uncertainties. Maybe the lead time is 6 to 8 months. I may have to deal with hurricanes and other forms of uncertainty. And I may have other decisions like, if there's a hurricane, I may do a rush order using air freight. Okay, so we're going to walk through the framing process, and I'm going to pause periodically and use this little example. So let's start with metrics. So anybody in business knows about KPIs, key performance indices. And often they have it by role. So if you're the CEO, you have a whole bunch of these. And companies, I've seen companies with just hundreds of KPIs. Now, I love to contrast this with the work of Laura Césaire. Laura Césaire is a deep thinker. She's a major influencer in supply chain management on LinkedIn. She has this book where she favors two metrics, operating margin and inventory turns, because from the perspective of somebody focused on maximizing the stock price, she says, okay, those are the metrics that really make sense. I like to put metrics in the form of a pyramid. Now, if you're working in the corporate office, interacting with the C-suite, maybe your top metric is stock price, but then below that, I'll go with Laura's operating margin and inventory turns, and maybe something for depreciation. And then you've got layers of metrics below that. So you want to prioritize and you want one at the top because that sets the units. Now, maybe you don't work in the C-suite. Maybe you're down in manufacturing and your top unit is metric is your unit cost. Now, you can form this pyramid for any context. Maybe you've been put in charge of a project. Hey, take the core goal of that project, put it at the top of your pyramid, and then fill in the other metrics that you do have to pay attention to. Now, in a company, you may have a whole pyramid of pyramids, and realize that when you're at one level of the pyramid, maybe you're an executive at the second level, one of the decisions you might make is to set the metrics for somebody below you. So these pyramids are very flexible, but what they should do is reflect the metrics that matter to you or your division or the group that you work with. Now, categories of metrics. I can't list all the metrics, but I can list categories. Right now, I'm up to 7 categories, and within each of those, there's tons of examples. Now, how you measure them, the first way you measure them is on average. How well are you doing per unit per month? What's your drug success rate? These are the averages. And then you have something that is generally referred to as risk. Now, a risk event is an event in English not reflected in average performance. So usually it's something extreme, and usually, but not always, it's something bad. Now, the risk metric quantifies that, and again, not necessarily in units of dollars, but in some quantifiable unit. So risk is simply quantifying events that are not captured in average. Now, performance metrics can be objectives to minimize or maximize. It can be limits, something that you want to stay above or below, or you can have targets where you can be above or below, but you'd like to be as close to the target. If you're familiar with the book The Goal, this is a classic. It came out in 1984, possibly the widest selling business book. And the core thesis of this book is metrics. It's taking a group inside a manufacturing plant that focus on all sorts of little operational metrics and saying, hey, you guys are focusing on the wrong metric. You have to look at more of a global metric. Now, for our inventory problem, maybe we put operating margin at the top, and then we have the second layer and the third layer. Now, these metrics give the entire project focus, okay? So this is going to then guide how we approach the other framing questions. So let's now go to decisions. So decisions is one of my favorite topics. First of all, I found it very hard to figure out what a decision is. In over 2,000 years, going back to the great Greek philosophers, I just can't find much evidence that we have an actual proper definition of a decision. Now, these are 8 of the greatest names in decision making. Now, if you look at the technical books, the deterministic optimization books, decisions X, so you just take X, and one of my colleagues says, well, everybody knows what X is. In stochastic optimization, they also have letters, but it's either X or action A or control U, but it's always a variable, and none of these books ever define a decision beyond simply having a variable. Now, a decision is a form of information. So let's take a look at information. There's what we know or believe at a point in time. That's our state of knowledge. We have new information coming in that I control, okay, where I control that information. And the third class is information that comes into the system that I don't control. It's from outside the system. So number 2, those are my decisions. So my fancy definition is an endogenously controllable information class, or my plain English definition is something we control or choice among a set of actions. Now, in English, there are many words for the term decision, and for people on this talk who come from other countries, I think we have a nice international audience. In your language, I challenge you, put together your own list of different words in your language that mean decision, okay? So, but this also means that if you go into talk to somebody or go into a company and try to ask a question like, what decisions do you make? Get ready for blank stares because you may not be speaking their language. This even happens when I'm speaking English, okay? So we have to be aware that this concept of a controllable information class is not something that everybody's trained to recognize. Now, this is, I consider my biggest, most recent achievement is to identify 8 types of decisions. And by the way, let me point you to a URL at the bottom, tinyurl.com. What is a decision? I've come up with 8 types of decisions. So the first type is the most common in optimization of managing physical and financial resources. A discrete action could be, should I sell the company or launch a new product. Number 3 is information acquisition. I'm going to decide to run an experiment or to call somebody or to hire a consultant. Number 4 is information sharing. This is messaging, marketing, and what channels and timing. The rest of these get a little bit more technical, but let me draw your attention to number 8, which is a very big decision, which is deciding what to decide. And when you start doing your list of decisions, you're going to realize, boy, there's a long list of decisions. And I'm not going to sit and worry about making all of them. Now, decisions are made over different time frames, from real-time, tactical to strategic planning. And they're made by different people, the C-suite managers, suppliers, customers, competitors, you. Now, this is one of my favorite slides. I was at a workshop sponsored by Amazon. And after the workshop, they took us out to one of their fulfillment centers. And so there's all this activity all over the place, very impressive. And I found myself saying, okay, let's make mental notes of where I see decisions. Now, there's design decisions that were clearly made when they designed the facility, and then there's operational decisions made on an hourly or daily ongoing basis. Now, this can arise in a warehouse or any other setting. Maybe I'm trying to improve hospital operations or do research on a new drug, or maybe I'm managing a forest. Now, what I'd like everybody to do is get a blank book. This is a red book I got from Amazon that just has blank pages. And what you do is, for any given setting, you have to write in, mainly I'm looking for the decisions, but also the metrics and uncertainties. And these are things that you have to do by observation. I claim this isn't as easy as it sounds. It requires training and practice. Now, I love this commercials that came out in the 1970s for V8 tomato juice. What this company, what I think was originally Campbell's Soup, realized is that you had a lot of people out there drinking a cola. Okay, they're drinking Coke or something. And they didn't realize that they could have made another choice, and that by drinking that soda, that was a decision. And so then they would feature somebody hitting themselves on the head going, I could have had a V8. If you go to YouTube and search on I could have had a V8, you come up with a bunch of these commercials. This was a brilliant set of ads trying to make people realize you made a decision. Companies have this all through the operations, hospitals. When you do something, did you have a choice, and could you have made a better choice? Now, for our inventory problem, and again, if you look at the URL at the bottom, tinyurl.com, PAL inventory decisions, you can get this spreadsheet. So I have a tab for decisions for an inventory problem. Actually, a simple inventory problem, but one with very long lead times. And here I have about 20 decisions on different time frames. And these are physical and financial and informational decisions. Now, you're not going to want to make all of these decisions. This is turning what may be a basic problem into something that's just a little bit too complicated. So I have another spreadsheet that you can download. This requires no math and no data. What you're going to do is you're going to put your metrics along the top row from most important to least important, just by judgment. And then down the column on the left, list your decisions in any order. I don't, at this stage, I don't really care, but list all your decisions. And then in each cell, put in H for high impact, M for medium, L for low, N for none, and fill out this matrix. Every time you put in the letter, the spreadsheet will fill in the color for you. So it's kind of a little bit neat, but this is very basic. Now, the idea here is, and again, no programming, no math, no data. Look at this. What you want to do is focus on the decisions with the highest impact on the most important metrics. Okay, and you're going to use this to say, okay, of this list of 20 decisions, what are the ones I really want to focus on? Okay, uncertainties. Now, In the world of supply chain management, but for any world, there's all kinds of uncertainties. The supply chain community, there's countless books all saying either something about risk or resilience, but really they're talking about uncertainties. Um, my contribution to this is I have a technical book, and in chapter 10, I list 12 classes of uncertainty, not from the perspective of an application, but from the perspective of models. And so you're going to take those 12 classes, and then for your application, so for example, here we have the 12 classes of uncertainty on the left, and on the right, if I'm working in a supply chain setting, by the way, you could have multiple uncertainties in each of the classes, but I just listed one just to illustrate. Now, if you're doing a supply chain, here's a set of uncertainties relevant to supply chain. If you're managing the power grid, here's a set of uncertainties for power grid management. If I'm doing something in public health, here's a set of uncertainties for public health. Now, this is just supposed to get you thinking about all the different ways uncertainties happens. But now I'm going to face the same problem with decisions. Oh, before I get to that, we also have to realize that uncertainty comes in different flavors. Hourly variations, bursts, spikes, systemic events, black swan events, contingencies of things that have never happened. So understanding the behaviors is a whole different dimensions of uncertainty. Now, if I go to my inventory problem, here I've listed again on a different tab all the different types of uncertainties that I could think of. Once again, it's a very long list, possibly longer than I want to really deal with. But again, we take our interaction matrix, which you can download from the internet, and fill it in and use this to say, okay, which of these uncertainties are most important in terms of their impact on the performance metrics. Okay, now I'm going to introduce you to the universal modeling framework. Now let me pause here briefly and say, by the time you've done framing the problem, this is a big deal. And I think that we should have people who have training in framing the problem. But when I go to the universal modeling framework, now we're going to see just a little bit of math. This is where we hand it over to people who are trained in mathematical modeling and have a comfort in that. These are people who would be very appreciative if you could come to them with the answers to the framing questions. This would be of huge value. I've seen endless projects where they build a big complicated math model that nobody can read, which hasn't done the framing right. They don't have the right metrics or decisions, and often they even ignore uncertainties. Okay, so the universal modeling framework, this is the slide in the lower right-hand corner. And by the way, the universal modeling framework, the whole framework is right there in that little box. What I'm going to do is use this PowerPoint slide. So it's one PowerPoint slide. This is the whole universal modeling framework. And we start with up here, any sequential decision problem can be written as the sequence of ST is the state variable, which captures what you know or believe. So this is what you know at time t, and it may be an estimate of something you don't know perfectly. Then there's the decisions. Now this is the information we control. And then there's information that comes in from outside the system. It's not known at time t, which is why it's indexed by t plus 1. Now, each time we make a decision, we compute performance metrics that depend on what we know and usually the decision. Now, decisions are made with a method called a policy, which we design later. This is my point of departure with the entire literature on optimization under uncertainty. I don't know how to make a decision yet. I'm going to get to that later. I'm just going to put in this fancy function. I call it capital X because I happen to be using X for my decision variable. And the Greek letter pi is the one that carries the information of what type of function. We will get to that later. Now, as I make a decision, I have my information st, I make a decision xt, then I have new information, and something called the transition function is going to say, once I know s, x, and w, this is the updated state. Now, state variables can be simple, but usually state variables can be quite complicated. So this formula, all it is all the equations saying how st gets updated. Now, the goal is to find a policy that optimizes performance over time. Okay, and this is also something that's often overlooked. Now, I'm going to take the math on this slide and rewrite it. So there's no new math here. This is all the same math. With this math modeling, I can model any of the problems on the right-hand side and in any of those complicated mathematical books. All of these books could be translated to this notation, and now everybody would be all speaking the same language. It would sort of be like telling the entire world to speak Chinese or English or something. So it's not going to happen, but young people can learn new mathematics, and I'm telling you, if you just learn this mathematics, you can model any problem. Now, I've got a new book that you can download for free. Go to tinyurl.com, Bridging Decision Problems. By the way, you don't need to remember any of these URLs. I will give you a link at the end. Now, this book, 150 pages and no math. Okay, this book is entirely about metrics, decisions, and uncertainties. And by the time you understand metrics, decision, and uncertainties, you have not covered the entire universal framework, but you've covered a major part, and you can't do anything until you answer these three questions. So these are the ones that need to be answered by somebody who is not trained in mathematics. Now, if you want to put this on the computer, I have an advanced book. This is a technical book for people who want to write code. So if you're the person who wants to build a model, that's the book for you. I'm sorry, I don't have a free download for that. Wiley won't let me. tinyurl.com RL and SO gives you a summary of all 20 chapters. Now, I am nearing completion of volume 2 of my new monograph series, which is entirely about modeling. In my big book, you go to chapter 9, which can be downloaded for free. In a few months, I will have, later in 2026, I will have, this is almost a 200-page book, and it does have math, but it fills in the details in much more detail. So let's get to designing policies, all right? So I've sort of said, I will get to that later. Well, later has arrived, and I'm now going to do this. So what is a policy? A policy is a method that makes a decision using the information in the state variable. Any method. Now, this is another one of these things where I know I have an international audience. In English, policy in the English language, I have almost 50 words here that in the right context mean how to make a decision, what to do in a particular situation. I've got this at tinyurl.com, policies and decisions. I have a Portuguese tab. Maybe somebody can contribute this in your home language. Now, there are two fundamental strategies for designing policies. The policy search is the first of them. Look-ahead approximations. Each of these divides into two classes, create what I call over and over again the four classes of policies. I'm going to start with the first of these. Now, the difference between policy search and look-ahead is policy search does not explicitly plan into the future. These are just functions designed to work well over time. And the look-ahead approximations do plan into the future. Okay, so let's start with policy search. So policy function approximations, the first of the four classes. So one is inventory problems, order up to. If the inventory goes below some level, order up to another level. That's a simple function. In finance, buy low, sell high. It's a simple rule. Large language models use a neural network trained to diagnose patients. Again, it's just a big function. Okay, it's a complicated function, but it's still just an analytical function. PFAs are lookup tables, they're linear, nonlinear models, neural networks, non-parametric models, any function you might use in machine learning. So the second class, cost function approximations. Now I'm going to divide these into two categories. In the first category, I'm going to assume that your decision X is something discrete. You have 7 choices. Which of the 7 choices should I make best? Now, an example of a policy, one of many, is to say for each of these choices, I have an estimate of how well it works. But I know it's not a very good estimate. So there's a lot of uncertainty, and I'm going to add in what I call an uncertainty bonus. Now there's a tunable parameter theta times the standard deviation. Now what I'm going to do is add these two together and then pick the best one. That's an optimization problem. Now let me tell you, of the 4 classes of policies, the first class, the PFAs, the policy function approximations, do not have an embedded optimization problem. It's the only one of the 4 classes that does not. All the other 3 have some form of an optimization. Now this optimization is nothing more than a sort, but that's still an optimization. And so what you're going to do is have this simple index. Now there are a number of ways to do this, but this happens to be one way, but you have the tunable parameter. Okay? Now, X could be a big vector of assigning machines to tasks, and I have to solve a linear or integer or a nonlinear program. Now, what happens is there's no explicit planning into the future, but I'm going to solve this problem over and over again, and I want it to work well over time. So often what I do is I put in bonuses and penalties, and everybody who works in math programming knows this. Everybody puts in little things to make their model work well over time. Now, CFAs are widely used in industry in an ad hoc way. Airlines optimizing schedules, they will put in schedule slack to handle delays. Manufacturers put in buffer stocks. The bottom one, grid operators that plan the electric power grid, when they plan power generators for tomorrow, they have to allow a buffer in case of outages. This is where I got the idea from. Now, so let's go to look-ahead approximations. And I like to use this image from The Wizard of Oz, where you have Dorothy and she has to figure out what path to go down. And you have to plan into the future. So this is not a problem where you can just use some simple rule, like always turn left. I mean, that just doesn't make any sense. So my third class of policy, let's say I'm a manufacturer down in Mexico, and I had to decide how much product that I'm manufacturing to send to each of the distribution centers. Now, what I have to think about is what is each distribution center going to do with the product? They have to satisfy customer demands, but I don't know the demands. It's highly uncertain. So what I'm going to do is create functions. This is the value of inventory in the future. These are called value function approximations. This comes from Bellman's equation. Anybody familiar? This is Bellman's equation. If you're not familiar, don't worry about it. It's not that widely used. But it turns a very complicated, messy problem into a very simple one. Now, the fourth of the four classes of policies is direct look-ahead approximations. And my best example of this is Google Maps. Here's a picture. So I'm up in the upper right-hand corner. I'm in Hartford, Connecticut, and I have to get to my home in the lower left-hand corner. And Google Maps gives me a path going right through New York City at 5 p.m. in the afternoon. And I'm like, Google, this is crazy. But what Google is doing is using a deterministic look ahead. So it's planning into the future deterministically. And you can say this is a rolling horizon procedure, but the control people call it model predicted control. And that's a deterministic look ahead model. Now, I might look ahead and go, wait a minute, Google, I'm not going to risk going through New York City. It could be really bad. I'm going to go around. And that's actually using a concept called robust optimization. Now, I'm doing that without any math. If you want to put it on the computer, this book on robust optimization is quite mathematical. Now, maybe I want to use decision trees or approximate dynamic programming or stochastic programming. These are entire books dedicated to how to plan into the future. So this gives you an idea that this fourth class of policy is quite rich. People get PhDs in one of the ways to solve a direct look-ahead problem. So this is why this is a jungle. Now, I might use a decision tree where here I have a decision, and the decision could be one of three things, or it could be a big vector. Then I have random things that are going to happen, and I have to make more decisions in the future, after which more random stuff happens and more decisions. So this is my whole stochastic look-ahead tree, and there's all kinds of various ways to solve this approximately. Okay, let's take a deep breath. I have covered the four classes of policies. The simplest are the policy search classes. I've covered the order up to inventory policy, or the simplest version of my cost function approximation, where I take a deterministic approximation with some tunable parameter. Now, the look-ahead policies, maybe I have the value functions, or I've got my Google Maps looking into the future. Or it could be my stochastic decision tree. Now, of these, three of these four classes of policies use optimization within the policy. And this gets very confusing because people will say, oh, I'm already optimizing and it's optimal. But if it's a policy, it's not an optimal policy, okay? And so you have to realize this. Now I'm going to make a big claim. These four classes of policies are universal. They cover every method for making decisions for any of the different types of decisions. It covers every method described in the research literature or used in practice. And it means that you are already using one of the four classes of policies or a hybrid in your own decisions. And there's a number of hybrids. Now, I'm also going to claim that you don't need to read a complicated book to learn these. Every human uses these in day-to-day life. Our brain somehow knows how to adapt to decision settings to make this. Let me illustrate with a nice little energy storage problem. I'm getting energy from a wind farm, but the wind is variable, or I can get energy from the grid where it's an infinite supply, but at very stochastic prices to meet this time-varying demand. And there I've got my Tesla Megapack to store up inventory where I can handle the variations. So with my old postdoc, Stefan Meisel, who now teaches at University of Twente, we created 5 variations of problems and then created 5 policies, the first 4 from each of the 4 classes, and the 5th one from a hybrid. And we created the problems to bring out the strengths of each one. We made each of these policies work best on one of the problems. So which of these policies you want to use is very problem and data dependent. Now, how do you evaluate policies? Well, it's not just which ones work best. This is not a one-dimensional problem. I've got 8 different categories of things that you want to think about, and all the metrics matter. And so you may say, well, one of these seems to work the best, but it's very hard to use, or it's very complicated to compute, and I don't have the CPU time. So this is why choosing policies is a much richer and more complex type of decision problem. Now, it helps to identify 6 types of policies. So we've got the first 3, the PFAs, the CFAs, and the VFAs. I'm going to take the 4th class, the look-aheads, and divide it into 2 subclasses, deterministic look-ahead and stochastic look-ahead. And then I'm going to take the stochastic look-ahead and further divide that between whether a decision is a discrete decision, like A, B, C, or one of 7 choices, or vector valued, okay? So which of these are most useful? Now, this took me a career to present this slide because I've had experience with all of these. Category 1 is easily the dominant category. It consists of 3 classes of policies, the PFAs, the CFAs, and the deterministic DLAs. This covers, 97% of all decisions, because all humans make decisions ever since we were, 2 years old, okay? Ever since we had any type of awareness and could say, no, I don't want to eat that. We've been using these 3 classes of policies. They're fundamentally built into the human brain. Now, category 2 is where I put decision trees. This is the stochastic look-ahead for discrete actions. And this is also widely used, but for more complex problems. So this is not an everyday type of thing, but this is taught in business schools, and business people use it quite widely. Now, category 3, which is where I spent a significant part of my career. I have a 600-page book. I've been 15 years. I describe it as a very powerful strategy for a very small number of specialized problems. This is where Bellman's equation comes in, and the academics love Bellman's equation. The problem is it's just not that useful. It's a home run in the right setting, but it's just not that useful in most settings. And then category 4 is where I do stochastic look-ahead with vectored value decisions, and this gets to be a real mess. This is highly specialized, and you need specialty training to do this. And it's not just one technique, but 2-stage stochastic programming is at the top of my list of the least used policies. Okay, so I'm going to close out my talk with some teaching materials. I'm going to start by talking about the field. Now, here's a nice little village, and the village has various shops. It's got a bake shop and a butcher shop and a grocery store, and there's Joe's Dairy. And so if I need meats or baked goods, I go into different shops. This pretty much describes the fields of optimization under uncertainty. Because what we've got is a whole bunch of shops, and every one of these books is its own shop, and it speaks its own language and has its own tools, and it can solve its own problems, okay? I would like to create the supermarket where you can go into the supermarket and you have everything. And so if you have a problem and you don't know the right method, you want to be able to go into a store and say, okay, what is the best method for my problem? That book full of methods, that library of books full of methods, those are books where they're like the proverbial hammer looking for the nail, where they have a technique and then they've identified problems where the technique works. That's not the way the real world works. We don't go running around saying, okay, who uses my big hammer? We have problems to solve and we need to use the best tool for that problem. So, the books that I have, this is my graduate level book. It came out a few years ago. It is made for an engineering audience. This is for people who are going to write code. And if you're going to write code, you're going to need this book because it will write out the equations. I spent a lot of time developing software and supervising software development. Now, when I taught this course at Princeton, at the graduate level, I had graduate students from 10 different departments. So in other words, this wasn't just the mathematically sophisticated departments. But it is, if you're going to write code, I claim you have to be able to get into this book and be comfortable. Now, I have another book I wrote for an undergraduate audience. Now, these were students in engineering. It does have math, okay? Now, this is a teach by example style book. Other than chapters 1 and 7, every chapter is simply a different application written in the same way with roughly the same outline. Each one illustrates the full universal framework in a variety of contexts. This book is very popular. I think I have about 18,000 downloads, and you can download it for free from tinyurl.com SDA modeling. Again, you don't need to remember URLs. I'll give you one at the end. Now, this is my newest book, and this has no math, and this is for the framers. This is for the people who need to go into an application and ask the right questions. And although I cover this in just a few minutes, indeed, this is 150 pages just on the 3 questions of metrics, decisions, and uncertainties. Chapter 2, I've got about a dozen different applications where all I have is a list of metrics, decisions, and uncertainties. It's very easy to skim. And so I recommend this. This is not just the lightweight book before you get into the math. This is for people who are never going to learn the math, but they're going to learn how to ask the right questions. And then they need to be able to use those interaction matrices to sort down, okay, here's 20 decisions, but what are the 5 that I really want to focus on? Now, I'm going to be coming out with a series of books over the next few years. Volume 2 is on the Universal Modeling Framework. It does have all the math, and then I will have a book dedicated to the 4 classes of policies. But instead of just rotating through the 4 classes, I'm going to go from the most useful to the least useful. And then Volume 4, I've penciled in that I'm going to work on multi-agent problems. I'm really excited about getting to that. Okay, so I have another URL, PAL framing video on this topic. Now, this link, tinyurl.com/SDA links, that's the URL that you have to write down. tinyurl.com/SDA links, because this is a web page of links. This is a resources web page, and I continually maintain this with what I think are the most interesting links. Okay, thank you very much. I've enjoyed talking to you, and Chris, thank you again for the invitation.